We now consider the general situation. So we can see we have k plus 1 points in n-dimensional Euclidean space, such that the difference vectors, the k difference vectors here, it's a linearly independent set. So if we so suppose we have origin here in the n-dimensional Euclidean space, and we have, say here, U1, we have U2, okay, we have U, k plus 1, and UK here. Okay. So this is the first difference vector, U1 minus UK. Oh, sorry, not this one. This is U1 minus UK plus 1. And this one is U2 minus UK plus 1. And this one is UK minus UK plus 1. So we have other many points. And here we assume this difference vectors form a linearly independent set. Okay, and then we find a subset of Rn to be that the point is represented as UK plus 1 plus T1 x1 minus xk plus 1 plus T2 x2 minus xk plus 1 plus Tk xk minus xk plus 1. Alright, and so this is, what is that? This is x, this is u, k plus 1 plus the span of x1 minus xk plus 1, x2 minus xk plus 1, up to xk minus xk plus 1. So we define. Okay? And H is called k-dimensional affine space A, F, F, I, and E in Rn. And it is called k-dimensional because we are using k-free variables as parameters, okay, to generate points in H. So, and it is called affine spaces because there is a point, a reference point, UK plus 1. Okay. So, okay, so that's all the previous examples are special cases of this definition. So a line in Rn, not only in R2 or R3, a line in Rn, it's a one-dimensional affine space. Rn. And a plane in Rn is a two-dimensional affine space in Rn. Alright, so any one-dimensional affine space in Rn called a line, and any two-dimensional affine space called a plane. And an n plus one dimension affine space. So when k is equal to n minus 1, just one dimension, less than the n-dimensional Euclidean space. So an n minus one dimension affine space in Rn has a special name, will be called a hyperplane. Okay, so a hyperplane. Okay, so let's take an example. Okay, so we let U1 should be 1 plus 1, 2, 0, 1. Okay. 2, 0, 1, 0, 2, 2, 3, 1, 0, 0, 1, 0, U4, 0, 1, 0, 0, 1. Okay? 4 points in 5. So they are 5 dimensions, so they are in the 5-dimensional Euclidean space. Alright? As we mentioned before, an n tuple here, we have 5 tuple. So a 5 tuple enclosed by parentheses is another way to write the column vectors. So every time when because this is much more convenient, right? More compact. Otherwise, if we write the column vectors, sometimes we'll need more space to write a statement. So let's see, we have 4 points, okay, in the 5-dimensional Euclidean space. Now we look at the difference vector. So U1 minus U4, U minus U4, we get 1 minus 2, 2, 0, 0. U2 minus U4, we have 0, 0, 0, to 1. And the U3 minus U4 equal to 1 minus 1, 0, 1 minus 1. Okay. All right, now it can be checked that these three difference vector U1 minus U4, U2 minus U4, U3 minus U4. Okay, it's a linearly independent set. Okay, and we have shown how to do the verification, okay, by solving a homogeneous linear equation, linear system. Sorry. All right. So we now have a linear independent set for this set of different vectors. So there is one, and only one three-dimensional affine space. Okay. H, right? H. Okay. Going through these 4 points. Okay, so so you can say that if these 4 points, satisfy the condition that this set of difference vectors is linearly independent. Geometrically, it saying that these 4 points is not coplanar. Because to determine a plane, you need 3 points. Remember, let's review Euclidean geometry. In any space, n-dimensional space, 2 points, 2 different points will determine one line, right? So 2 points will determine a line, which is one-dimensional affine space. Now in Rn, if you have 3 points, if they are non-collinear, if they are collinear, then the 3 points will be on the same line, right? And then you cannot determine a plane, just a line only, right? So if you have 3 points, they are non-collinear, then they can determine a plane. And a plane will be a 2-dimensional affine space. Okay, and we demonstrate that for 2-dimensional space and R2 and R3. R3 already. Now, for here, we have 4 points. So this 4 point is non-coplanar. Coplanar means that the 4 points will be in the same plane. Coplanar. Okay, so this indicates that the statement here, okay, is equivalent to saying that U1, U2, U3, and U4 are non-coplanar. Okay, so they are not linear. Okay, sorry. Alright. So non-complainer. You may argue that if these three difference vectors is linearly dependent, if they are linearly dependent, then we can show that these 4 points are in the same plane. Means that they will be in the same 2-dimensional space. But we will show that by a theorem. Okay, so I will give you a theorem to explain that. Okay, so anyway, this is a geometrical statement, but we put the statement in terms of the language in linear algebra. It is saying that this set of difference vectors is linearly independent. Okay. All right, so we checked that already, right? So you can check the factor. Okay, and so that the edge here is so the 3-dimensional affine space is U4 plus P1, which one? It's U1. It's U1 minus U4 plus P2, U2 minus U4 plus P3, U3 minus U4. So now, X in this 3-dimensional affine space, if and only X can be written here by U4 plus P1, U1 minus U2 plus P2, U2 minus U4 plus P3, U3 minus U4. Okay, for some P1, P2, P3 in all. Okay, so X is a point in this 3-dimensional affine space. If the only if we can express X by this expression. This is from the definition. Okay, and so we can rewrite this vector equation into matrix equation. So we have U2 minus U1 here, the first column, U2 minus U4, 1, U4, and the U3 minus U4 together, and the P1, P2, and P3, and equal to X minus U4. Okay. So this is a common vector. So this is a common vector. Okay. And it's 5-dimensional, so we have, this is 5 times 3 matrix, this one is 3 times 1, and this is 5 times 1. Okay. And this is a linear system. And because that there exists the P1, P2, and P3 are satisfied this linear system, So it's consistent. Okay? So it is consistent. Alright, and for this specific example, we now write the augmented matrix. So it's 1 minus 2, 2, 0, 0. Okay, 1 minus 2, 2, 0, 0. And then 0, 0, 0, 2, 1. 1 minus 1. 0, 1 minus 1. And we have x1, we have x2 minus 1, x3, x4, and x5 minus 1. So this one is here, is x minus x4, x minus x4. And the x4 is 0, 1, 0, 0, 1. So x minus x4 makes x1, x2 minus 1, x3, x4, and x5 minus 1. So it's consistent. Right. So this is the augmented matrix. It's okay, and now we proceed Gaussian elimination. Okay. So by elementary operations, we end up with. So let me skip the details. All right, 1, 1, 0, 1. We can. This is x1 and then 0, 1. So this is pivot minus 1. So we have x5 x1. Just by moving the last row to the second row. Right? So we can say that we can just swap the second row and the fifth row. Okay. And then the rest will be here. We have x2 minus 1 plus 2x1. Okay, and now we can do all the eliminations. So let me just I think this is correct. This is minus 1. Okay, so we have x1, x5 minus 1, and here by elimination. So basically, well. So we have x2 minus 1 plus 2x1, x3 minus 2x1 plus 2x1. Okay. All right. So this one after the elementary row operations. All right. So this augmented matrix is consistent. Now, to be consistent, we have to require that these two entries are zeros. So if and only if that well, we have 2x1 plus x2 plus x3 equals 2, and minus 6x1 minus 3x2 plus x4 minus 2x5 is equal to minus 1. Alright, so starting with a point in this three-dimensional open space, we know that if and only if that the points, coordinate of the points to satisfy these two linear equations. Okay, we have five variable unknown variable here because h is in R5, right? It's 5-dimensional. Okay, so the conclusion here is that the three-dimensional open space H in R5 can be represented by a system of two linear equations, right, with 5 unknowns. Okay, so we have this conclusion, but this is a specific example. Alright, so even though it is just a specific example, but now we can state a general theorem, 2.2.c, a k-dimensional open space H in R5 can be represented by a system in Rn, sorry, can be represented by a system of n minus k linear equations Alright, so by a system of minus k linear equations with an unknown. So the proof is an exercise. In this derivation, that as I mentioned last week, and for this case, that because these three columns are linearly independent, these three columns linearly independent, right? Because they are different vectors, and because it's three-dimensional, we assume they are linearly independent. So, by a theorem in chapter 1, okay, so we must have three pivots. Means that we have a pivot in each column. Okay, so this is a pivot, this is a pivot, this is a pivot. And since we have pivots, three pivots here, so that we have 5 minus 3 rows, right? They are all zeros. Yeah. So the corresponding entries in here and there must be 0. So that's why we have 5 minus 3 equals 2, two equations. And so when you do the proof of this theorem, you will use the similar argument as here. And more important, more important is the theorem 2.2.b. A system Ax equal to b of a minus k linear equation. Okay, with an unknown. Okay, so this one, this is m minus k times n plus 1, m minus k times 1. So a system of n minus k linear equations with n unknowns represent a three-dimensional affine space. Okay, so once we have such a system to present a three-dimensional affine space in Rn, if and only if the rank of A, the rank of this coefficient matrix is equal to m minus k. Okay, so let me give a proof of this theorem. Alright, so first of all, we let U and C be the reduced row echelon form of the augmented matrix A, B. Okay, so this augmented matrix corresponding to this linear system. Okay. Now it is clear that U is the reduced row echelon form of A. So because it's augmented, we have one more column. Alright, then the original coefficient matrix A here. So if we do the Gauss-Jordan evaluation on the augmented matrix, and then we get this reduced row echelon form of this augmented matrix. And in the process, as we pointed out before, that U should be the reduced row echelon form of A. Okay, so any questions? Okay, so this is the starting point here. Now we would like to show the reverse direction. Alright, so we want to show that given that the coefficient matrix has rank equal to m minus k, then we will show that this linear system represents a three-dimensional affine space. Okay, so we do this direction. Now, so since rank of A is equal to n minus k, okay, so they are n minus k fields in U. Okay, so we have, but in this reduced solution form, specifically in U, we have n minus k fields. But we have only n minus k rows, right? Because the dimension here, so the A is n minus k times n, and B is n minus k times 1. So U is n minus k times n, and this is n minus k times 1. So even though the UOA have n columns, but they have only n minus k rows, and the knowledge that the rank of A equal to n minus k, so alright, so we have n minus k fields. So now without loss of generality, we assume, right? So we assume that the first n minus k columns okay, of U contain fields, and the rest k columns do not. Right? So i.e. we can write down this 1 and 0, 1, 0, 0, 0, 1. Okay. So 1, 0, this one just like an identity matrix. Okay. And here we have U 1 n minus k plus 1, U1n, U2 n minus k plus 1, U2n, U n minus k plus 1, U n minus k, okay. C1, C2, C n minus k. Alright, because we have n minus k fields, so n minus k out of the n columns should have fields. And then for this specific case, we just assume the first n minus k columns of U contain fields. Right? Because I want to write down a matrix specifically, so and make this a sum. But this is without also generality, right? We can back to so for example like this one. Okay, so now now we can for any variables, okay, corresponding to columns with pivot. Because they are pivot, right? We can select them as dependent variable, right? As we saw before. And variables, okay? So they are variable corresponding to columns without any pivot. Can be selected as free variables or independent variables. So they are free variables. Right? And we select them as dependent variables. Okay, this is our selection. This is a common selection. All right. So now we have x1. So now x1 can be written as c1 minus u1 and minus k plus 1 x and minus k plus 1 minus minus u1 and x and okay. The first equation. The first will let you express x1 by using the free variables xn minus k plus 1 up to xn, and x2 the second dependent variables comes to c2 minus u2 minus k plus 1 xn minus k plus 1 minus 2n up to xn minus k, c and minus k minus u and minus k and minus k plus 1 x and minus k plus 1 minus u and minus k and xn. Alright, so and the solution set of the linear system Ax equal to b consists of all vectors Rn of the form okay, so let me write down the form here. x1, x2, maybe xn minus k, xn minus k plus 1, xn. Okay, so the first n minus k variables are dependent and can be expressed like that. And the last k variables are free or independent variables. Alright, so let me copy here. All right, and up here, C and minus K. And here we have x and minus K plus 1. Because they are free, so we can select them arbitrarily. Okay, and now, so the constant vector here, and we will select the free variables as parameters, right? So the first parameter is x and minus k plus 1. So anything related to this free variable will be put in here. So now we have 1 minus k plus 1 up to u minus k plus 1 and 1. That's 0. Alright, up to the last three variables. Okay, so x is expressed here. And here we have k vectors. All right, k vectors here. So where xn minus k plus 1 up to xn. Are parameters, and we can see that the k vectors right, the Q vectors form a linearly independent set. Why? You can look at the button. This is n minus k, the size here is k. Suppose you form a linear combination of these k vectors, okay? If you form linear combination of these k vectors, say alpha 1 times this vector plus alpha 2 times the second vector up to alpha k times this k vector. You will see that will form the linear combination. Okay. But if you have such a linear relation, all right, it will implies that the left-hand side becomes to something, okay? But here is alpha 1 up to alpha k. The first MISK components can be complicated, right? So I just write some arbitrary. Okay, I use the while character. Okay, yeah, to indicate there can be anything. But the last k component will contain alpha 1, the coefficient here, alpha 1, alpha 2, up to alpha k. Right? Because here 1, 0, 0, 0, 0, 1, 0, 0, 0, something, right? So you just move alpha, the coefficient here. And this is equal to 0, 0, and 0, 0. So this means that alpha 1 equal to alpha 2 equal to alpha k equal to 0. So any linear relation implies that the coefficient should be zeros. So that means that this k vectors is a linearly, they form a linearly dependent set. Okay, by our definition. So now we have from like this one, we have a constant vector here. We have parameters, k parameters, and the corresponding vectors are linearly independent. Okay, so by our definition, it's so that it's a k-dimensional affine space. Right? So this shows that the solution set of the linear system Ax equal to B is a k-dimensional affine space. Okay, so we finished the reverse direction. Okay, so the proof is just solve. We solve the linear system explicitly. All right, and give you the set of the solution set and indicate that this is a solution set indeed form okay, a k-dimensional affine space. Okay, showing that we have free variables, k free variables here, and the corresponding vectors, the k vectors are linearly independent. Any questions about this reverse direction? Okay, so now we will prove the forward direction. Forward direction means P implies Q, right? But logically, we all know that they are equivalent to negative Q implies negative Q. So we'll take this approach by assuming that negative Q means, what is negative Q? Negative Q means that the rank of K is not equal to the rank of A is not equal to M minus K. Okay. So we now assume, we now suppose that sorry. assume that rank of A not equal to n minus k. Okay, so this is not Q, because Q means Q state that rank of A equal to n minus k. Alright, and so we have to prove that not P. What is not P? Not P means that the solution set of the corresponding linear system is not a k-dimensional affine space. Okay, so we will follow this approach. Now, since A has n minus k rows, the rank we denote it as R of A, denoted as R, must be, because A has only n minus k rows, so it can only contain at the most n minus k pivots. Okay, so the rank is at the most n minus k. But now, the rank is not equal to n minus k, so the rank should be less than n minus k. So the rank must be less than n minus k. Alright? Alright, so then the first rows of U. The first row of U. U is the reduced row echelon form of A, right? So the first rows of U contains pivots. And the last n minus k minus r rows of U are 0 rows. Alright, so let me draw a picture. Here. So this time we have only so the dimension here we have only rows contain pivots, and the rest of them are all 0. Alright, and here we have U1 plus 1, U1n, U2 plus 1, U2n, UR plus 1, URn, and 0, 0. This is the R, and suppose we have this situation. Okay, so this is what we know. Okay, so so the rank, because the rank of A is R, and so the first R rows contain pivots, but the last n minus k minus r rows of U are 0 rows. They are all zeros. So here we have n minus k minus r rows. Yeah. They are all zeros. Okay, and here will be arbitrary 1. But the last column, the last column here. That so again our result. Okay, so without loss of generality, we assume that the first columns of U contains pivots. Alright, like this one. So as before, okay? Because we have our pivots. So n columns, all of n columns, we have only our column pivot. So and we assume they are in the first columns here, like this one. Okay, it's about the arrangement of the U here. But how about C, the last column? You know that because our system is consistent, so so if but we cannot draw out the entries here. So so let's see. So if the last column C of the augmented matrix UC contains, right? Contains a pivot. Alright, so if it contains pivot. So if it contains the pivots, that means that one of the entries here must be non-zero. If this is the situation, okay, so then the linear system is inconsistent. Alright? So if any of the entries here is non-zero, then this augmented matrix corresponding to an inconsistent linear system, and you have no solution at all. No? So and the solution set, alright, is the empty set. And in this case, of course, that the linear system, right? Ax equals b does not represent any k-dimensional affine space. Okay, so if the entries here is non-zero, means the last column contains a pivot. Okay, then the linear system is inconsistent, and the solution is empty set. And so, of course, it does not represent any k-dimensional affine space. Alright, so this case has been considered now. So, and the second case is that, and if the last column C of UC does not contain any pivot. So in this situation, the entries here must be all 0. Okay? So the second case is that the entries here are all zeros, and so the linear system is consistent. So we have a solution. Okay? So does not contain any pivot. Then the linear system AX equal to B, alright, is consistent. Right? It's consistent. And in this case, the x1, x2 up to xr, they are all dependent variable. Okay? And xr plus 1 up to xn, they are all free variables. Okay, so in this case, as illustrated, all right, in the proof, of the reverse direction, okay, previous. The solution set, okay, of AX equal to B, okay, it's an n minus r dimensional affine space. Okay, in n. Alright, so now this linear system will end up with an n minus r. Okay, because we have n minus r free variables. So the dimension is the n minus r. Alright? Since n minus r is greater than k. Okay? Because n minus r is n greater than minus n minus k. Why? Because r is less than n minus k, right? So r is less than n minus k. So n minus r is greater than n minus k, which is equal to 2. So again, the linear system AX equal to B does not represent any k-dimensional affine space. Okay, and we complete the proof because we proved not P, right? So we start with not Q here. We show the not P in two cases. Either we have non-zero entries here, so the solution space is an empty set, or if the system is consistent, then we have end up with an n minus r dimensional affine space, but n minus r is bigger than k. Okay. So we complete the proof. Okay. And so I have to finish here, and we will have a third quiz explanation. So, any questions?